information, this distribution will change. And all you want to argue eventually is just you don't change this distribution more. Which means that with respect to this individual, you learn nothing, right? And so that's to a large degree why, for example, zero-knowledge proof cannot be developed earlier, in part because people don't have this sharp language to say that you have a protocol, this protocol did something. What do you mean it's absolutely secure? And is this nature of definition basically said that you have to be secure against the spec output, right? If the election protocol is only to decide the final tally, you have to assume that tally is given, right? So clearly the tally is given will induce a different distribution from the uniform distribution, right? The moment tally is given, clearly the election is not flip coins anymore, right? And for a while, I think people don't have a accurate language to describe such a thing. And this is also why you can see once somehow one definition gets clarified, either encryption or pseudo-randomness, then suddenly many other definitions get clarified, because they look back and say, oh, we should just define this way, right? And the body of knowledge, for example, for security and privacy are also divergent, right? Because it really imply different things. So that's why, if some of you pick up the differential privacy thread, beautiful, they have their own limitations, but it did capture a lot about the what's the limit you can change the data so that your data still are secure enough to be released. So the main motivation is publicly release our record, and in which way you can put in so that you can say it essentially protect everyone's privacy. So it seems that we have a slightly smaller house today. So today I just have a simple agenda. I will go over the RSA and also its surrounding adversary elements. Right. So last time we talked about essentially the basic property of groups. Right. A group is technically it's not much, but it's just remarkably useful in other sections of mathematics. So a group is just a collection of elements that they are evaluated based on a particular operator. And you just have all the properties that you wanted to have, namely closure property, when you take two elements. When you multiply, you have in the same set. You didn't create anything beyond the group. And then basically just introduce very basic structure, namely you can take an inverse of elements. Right? So namely this inverse essentially gave you an automatic sort of a bijection map in your domain. Right? So everything has a bijection map called inverse. Okay? So that's essentially the only structure there. But what is useful is that when people begin to examine other mathematical domains, they see such a property arise, and they can use the language of a group to establish properties. So for example, one of the main properties we use is Lagrange. So Lagrange theorem of group basically said that if you have a group, and if you can create a subgroup, then the subgroup is not arbitrary. It has essentially just what we intuitively think is a subgroup is a unique modular of all the group. So all the group can be divided into modulars with image of subgroup. Right? So for us, one of the particular subgroup that utilize for public key encryption is called exponentiation. Okay? So when you take exponentiation, you can take any group element in a group, and then you can raise it to high power. Right? And if G is finite, then this has to be finite, just by definition, because you never create elements beyond this set. And it's very easy to check this has to be subgroup, because it's closed on itself. Because multiply, when you have gx times gy, and this thing, they all commute against each other, and so clearly this eventually just becomes gx plus 1. This is exactly what we think about exponentiation, right? The exponent just become additive, right? So that's why this is a subgroup. And so this simple fact basically immediately implies the following, which is very useful. That is, for all g to the power, the side of original group is equal to 1. So this is a Lagrange's equation. Okay. For every element, there is a particular operation somehow making it all uniformly point to 1. Right? Because you just need to raise the group size, then it will give you the 1. Right? And it used to be stated very innocently. You know, when we learn group theory very quickly, this is proved. And because it's elementary proof, and usually sometimes assigned homework. And for us, basically, such equation eventually will take an information meaning, right? So this is really what I call so-called the ability of doing research, is that to pull the connections between your current problem and what people already know, right? Because each generation has their own problem. They will put all the mathematics or physics or chemistry into different lens, right? And hopefully that lens will give you a new solution to the new problem. So one of the group that we'll consider a lot is what we call multiplicative group, Zn star. Okay. So Zn star is basically the set of elements of X, then the GCD X and N is equal to. Okay, so this is what we define as Zn star, and the operation we are going to use is multiply. We are going to multiply numbers. Okay, so if I give you mod n, so this everything was done by mod n, right? So within mod n, I have a collection of elements. Some has GCD against n maybe not equal to 1. But we are only interested in the elements that has GCD equal to 1. Okay. So the property of this, if we use the group, the multiply, is that this whole thing defines a group. This whole thing defines a group, what we call the multiplicative group of mod n. Okay. And the reason why this defines a group is following. We know that. If GCD xn equal to 1, GCD yn equal to 1, then we knew that GCD xy times y n is equal to GCD y times x n, so this is equal to 1. Right? Because we're just counting factors, right? If x has no common factor with n, and y has no common factor of n, when you multiply them, you're just collecting the factor. This is like set union operations, right? Because when you multiply two numbers, the prime factor is just unioned. You take unions of factors. So which means that if in this collection of union factors, you can't create a common union factor against n. If neither create, then clearly the union couldn't create. Right? So this is basically trivially true just by the first principle of n can be written as a product of a prime to some power, and each x and y can be written as prime to some power, and then this just becomes set operation. That the GCD just say whether the two sets intersect or not, and clearly if you just multiply, that should take union. Right? So that's the mathematical proof, and this proof shows that this thing is closed. Right? It's closed. When you multiply, it's still there. You did not put it outside this collection. The rest is proof is trivial, right? Because it's just numbers. So clearly, it's associative because multiply is associative, right? And because the Euclidean extended Euclidean algorithm, or we call Bayes' theorem, we knew that everybody here has inverse, just by Bayes' theorem, which we did last time. Everyone has inverse here. So because x has inverse in the n star, if GCD has n equal, right? So because it's if and only if condition, then this automatically says everybody has inverse, and that's the last condition to give you the group. Okay. So this will be the group that we are going to study a little bit. So that's why let me just give you a simple example. Let's just play a little bit around. Okay, let's just play a little bit around to get a certain sense of what they look like. So for now, let's consider n equal to 15. Okay, so equal to 5 times 7, 5 times 3, n equal to 15. Okay, so let's consider this again, 15. Right. So let's first look at what is the n at d15. D15 basically is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That's the 15, right? Did I miss a number? No. So if you look at this, we can almost quickly mark out what has GCD equal to, not equal to 1, right? So does GCD of 0 against 15 equal to 1? No, it's equal to 0. Does GCD of 3 against 15 equal to 1? No, it's equal to 3. And 5 clearly disqualified because it has 5 in it. And 6 disqualified because it has 3 in it. And 9 disqualified because it has 3 in it. And 10 disqualified because it has 5 in it. And 12 disqualified. Okay? So, based on this definition, the n star is basically is a 1, 2, 4, 7, 8, 11, 13. So how many numbers are here? 8. Right? 8 numbers survive this filtering of GCD. Okay? 8 numbers survive GCD. And I would like to eventually relate it with one of the theorems that we are going to establish, because that theorem will allow us to later on look at pseudo-random number generation with much clarity. Okay? So let's just organize those numbers a little bit, right? Because if you really think about D15, and in some sense we are doing certain what do you call assembly of the numbers, right? Against this 2 prime factor, right? So let me first write down the following table, and just see how they laid out. So let me create a 15 3 by 5 table. 3 by 5. So how do I do 3 by 5 table? I do 3 here, 1, 2, 3. Right. So let's put the 15 table all here, right? The number here. So let's look at this collection. So let me assign this to be 0, 1, and 2. So this is my Z3, right? My Z3 0, 1, and 2. And let's give this coordinates to be 0, 1, 2, 3. So this is my D5. Right? So, so let's just put a number here based upon the following map. Let's create the coordinates. So somehow we go from one-dimensional data into two-dimensional data. Let's just give it coordinates, right? So let's give it a simple map. That is, I would like to map f of a number equal to x mod 3 and x mod 4. So let me do this simple map. Because we knew this number is made of 3 and 5, and let's just see how they mod out against 3 and 5. Okay? So where should 1 go? Where should 0 go? 0 will go to coordinates 0, 0. Right? So 0 go here. Where should 1 go? 1 go to coordinates 1, 1, right? So this is actually 1 go. So you can see actually when I'm writing, I'm really wrapping around, right? So where do 2 go? So where do 3 go? Actually it went here, right? Agree? Where do 4 go?
1, 4.
Where do 5 go?
Goes back to his.
You have to go here, right?
On top, right?
Agree? Where does 6 go? Here. Where 7, 8, 9. So you can see, I'm really writing it by wrapping them around on this table, right? Where do 10 go? 9, then go here, that's 10. Is it correct coordinates, right? Is 0 against the second coordinates, and 1 against the first coordinate, okay? 11, 12,
and then
13, 14, right? So you can see I filled this table, actually I didn't have collisions in this particular writing. Right? When I mapped those numbers into these tables, there was no collision. So this is a bijection, at least with respect to 3 and 5. So this is a bijection. Agreed? I just, at least for these 15 numbers, I did a bijection, right? Because I did it in front of you, I didn't cheat, right? I did literally. But you can also see some of the pattern it went, right? Namely, if you lay out this as a coordinates, you know you have to go out this way, basically increase number, right? So the mostly motion is diagonal. But when you move out of it, you just move, because it's mod 3, you can see the impact of mod, right? It just wrapped to here again, right? It rises again, right? Okay. So one thing I like about this table is that if you look at where did the Zn star went, they went precisely to this range. So this is your N star, right? Because this is 5, 10, 0, they all multiples of 5, and 6, 12, 3, 9, they all multiples of 3. So clearly they flunked the GCD test, and neatly the rest put in the rectangular table. Right? They were put in rectangular table. And you would think it is clearly correct, right? Because those are the only thing with factors, and this is the only thing with factors. So 15 is clearly the only one with 2 factors. That's why they landed here, right? Right? So this is literally this collection, right? 1, 12, 1, 2, 4, 7, 8, 11, 13, 14, right? 1, 2, 4,
7,
7, 8,
13,
13, 14, 11, 13, 14. Okay? So you can see this actually is a cool layout of the data because it creates 2 coordinates out of 1 number. Right? It's really like a sort of 2-dimensional realization of number. And the other place we normally see 2-dimensional realization of number is complex. Remember our good old friend, complex number? It's really a 2-dimensional number, right? You said here is a real component, there's a imaginary components, and then we make the multiplication table so that the division is also behaving nicely. Right there we have every non-zero element has a inverse, and eventually I think it leads us to discover, for example, E, right? Because E is natural log E is become very naturally come out from the periodicity of that complex number. Right? So here, in many ways, is really the rich structure of number theory. That is, when you mod a particular number, they create a different dimensionality of data. So basically, the nature of n defines some sense of dimensionality of data. Okay? Nature of n defines the dimensionality of data. And this is what often we call Chinese remainder theorem. So this is what we call Chinese remainder theorem. That essentially, to formalize this to all mod n. Okay? To formalize it. So Chinese remainder theorem basically is that the fact that the odd entity in this square, for this case, is not an accidental case, it's a general case. Okay? So there are several versions of Chinese remainder theorem, but let me state the one which is closer to this layout, and then basically we can just do induction to get it final layout. Okay? So Chinese remainder theorem states the following. It states as following. Suppose a number n can be written as pq times q, where PCD of PQ is equal to 1. Suppose we can write a number into a product of two numbers that are relatively prime. Right? So then I can clearly use this as inductive purpose now. But that's me for now. So this is as close a map to here, right? Because I said 15 is written as the product of two primes. But it doesn't have to be two primes. Currently, I just say they're relatively prime. So for example, suppose I can write another number 30. I can write it 6 times 5. That's fine, right? Because that's covered in such case too. Okay? So relatively prime is only same matters here. So then basically, the first statement of Chinese remainder theorem is following. That this particular map, f(x) equal to x mod n mod p and y x mod q. So this particular map, I think I should write it this way. This particular map is bijective between Zn and so this map is a bijective between Zn and Zp times Zq. So it's literally this map. A bijective map between the two. So secondly, this f is also a bijection between Zn star, Zp star, and Zq star. So the first statement basically is corresponding to when I put the 15 numbers in, I didn't have collision. That's that statement. I put in the all 15 numbers in, I didn't see collision. The second statement is corresponding to my notice here, that the Zn star showed up neatly in this upper grid. The only layer you remove is here. So they need to show up in the upper grades. Right. So clearly these both maps are used the same natural coordinate creation. And third, which perhaps is more importantly, in both cases, the map is isomorphic. Define an isomorphism. In the first case, this is against the plus. And in the second case, is against times. So it's isomorphism with respect to add and multiply. Okay, so this is the main statement of Chinese remainder theorem. That is, if you can break down your number into two, and these two-dimensional coordinates is genuinely, universally true, that you can always write your original number, you fill this table cleanly, and then if you remove the first row and first column, or the lowest row and the leftmost column, and whatever left in that table is precisely the n star. It actually captured that correctly. Okay, it actually captured that correctly. So the only condition is that PQ is equal to 1. They're relatively prime. No, they're relatively prime. Okay? And more than that, this is isomorphism. And later on, I will heavily use this isomorphism to draw your intuition. Because it is much easier to think on those categories than globally. Because globally, mod n is far more complex to think. Okay? And more than that, if we recursively use this, this really is a defined so-called natural dimensionality of number, right? Because if n has k prime factors, because every number can be written as a product of prime and their powers, right? If n has k of such a thing, then essentially z mod n is just k-dimensional table, right? It's a map a number into k-dimensional coordinates. And this map is just genuine. It keeps all the mathematical structures of add and multiply, right? Clearly, it also keeps the structure of add together with multiply, right? Because it keeps both of them, right? So that's why this not only keeps the group structure, but also kept the later on the field and ring, these type of structures. Okay. So this is the Chinese remainder theorem. So let me give a very quick proof of this. It's actually utterly trivial to prove such a thing. And I think probably it was alluded to Chinese remainder theorem. Historically, that name is China was about 2,500 years ago was almost like Europe from a few, maybe 100 years ago. So China, I think, started with close to 100-ish states. They have many little kings. And in fact, my last name, Teng, was a kingdom's name. And unfortunately, in the first round of fight, they disappeared. So that's why we are a very small family name, probably because of the first round. So we used to live between mountains and the ocean in a province called Shandong province. But in the first round, it's gone. And eventually, Chinese history led to basically after all of 100 states, it's just like merging. They built a hierarchy, right? They merged. The state, the country emerged. And eventually, they had like 7 states. That lasts for a very long time, actually. The 7 states last for, I think, close to 1,000 years, until somehow one of the states become very strategic. They make friends with their, so before basically when they have alliance, they make friends with their neighbors. They make alliance with their neighbors so that they can fence off the invaders from far away. So suddenly one of the bigger countries said they want to sign peace treaty with a country far away. And they don't sign peace treaty with their neighbors. That's one dynamic somehow changes Chinese history, because it allowed the big country to fight their neighbors. Their far away alliance didn't intervene. So by the time it happened, there's only like a couple of states left there. So during that time, they have a lot of sort of layout of books about how military fight, lay out the troops. And I think this table, sort of table, showed up in one of the military books, in which way troops can be reconfigured, right? Because at that time there's nothing flying, right? Everything was really a real human fight at that time. They have to really line up troops to make sure they're robust when the other troop is pushing forward, right? So those are corresponding to when you model certain things. These are the military units, right? They try to reconfigure those, right? So I think during those time, many precursors of image of tables, like modular arithmetic, showed up in that book. I think that's probably the tribute to eventually the name called Chinese Remainder theorem. Okay. So let me quickly prove this. It's actually a very simple proof, but the reason I want to include this particular way, not the one in the book, is because remember I started my first lecture called "The World is Built Upon Linear Algebra." This mere scheme is really linear algebra, right? And here, in some sense, the proof of Chinese theorem is also linear algebra, right? Because once you have dimensions, coordinates, what do we have? Linear algebra, right? So you can see this actually is totally just linear algebraic thinking. And this function, what is this function? It's just a function create the coordinates. So what is our knowledge of function create the coordinates? We call projections, right? In linear algebra, the projection create coordinates, right? Remember that we usually have the native coordinates, right? Our x, y, z in 3D, right? We say the x coordinate, the y coordinates, and z coordinates, right? But imagine that someone came from from space. They came disoriented. They have their own coordinates. Usually we said we just wrote, it's like a transformation of current coordinates, right? But in order to create so you can, this is also coordinates, right? If I draw correctly in 3D, right? As long as they are orthogonal to each other. And they clearly have an old vector representation in our universe. But in order for any vector to be expressed here, you just do a dot product against these vectors. That gives you the coordinates. That is called projection. Okay? So this function is nothing different from a projection function. Right? So in order to have projection function, we have certain set of dot products. Okay? So let me write down the proof. And this basically is enough for us to look into not just RSA structures, but also subsequent work on pseudo-random number generations. Okay, so that's why this Chinese remainder theorem, it gave us a way to quickly look into those mathematical structures. So let me go with the condition here. Because we know GCD P, Q equal to 1, right? What does this mean? It means P has inverse in mod Q, and Q has inverse mod P. P has inverse mod Q, and Q has inverse mod P. So let's define this. YQ, so let's say YP is equal to P inverse mod Q, and YQ Q inverse. Right. So let's give this. So this means that. So what does this mean? It means YP times P is equal to 1 mod Q, and YQ times Q is equal to 1 mod P. Right? This is just directly from GCD. The moment that GCD equal to 1, they are relatively prime, then you can have multiplicative inverse, which means they exist. You can just write it out. Okay? So let me write out to prove something is bijection, the simplest way to prove is they have inverse function, right? Namely, I want to write an inverse function. You can see this is a little bit more complex than this. I want to write an inverse function to go from here back to here. I want to point to 1, 2 to 7. That's my inverse function, right? My inverse function, I look at this coordinate 1, 3, I said 13. That's the inverse function, right? My forward function is create coordinates, and my inverse function is going the other direction. I want to point a particular entry in the table, and you have to give me the number in the original mod. Okay? So this inverse function, so let me push this one here. So this inverse function, so let me define inverse function for a row. So this inverse function will take two coordinates, A and B. I want to map this from ZP times ZQ back to the end. Right? So this is my job to go back. Right? To go from the table into the original one-dimensional line. Right? So before we have these one-dimensional numbers, and my f function made them into two dimension, and this function I want to go from two dimension back to one dimension. Right? And here basically, if you really think about it, it's almost trivial. That is, clearly you have to use A, and the other map is linear map, so clearly you have to use B, and ultimately you have the mod N, right? So clearly there's a formula like this, right? So let me put it in between a little bit. Okay? So how much A we need to put in? Now we have to figure out how many copies of A we need to put in. And this is really governed by this equation, right? Because we say that we need mod P equal to 1 multiplied A. So this actually tells you how many copies you need to put A. So you just simply say YP times P. Sorry, you have YQ times Q. So this is how much copy of A you need to put in. And here basically you need to put YP times P. So why this is good? Because this is exactly what I call projection. And so when you try to mod A, if you try to mod P, that's your first coordinates, right? From this number you have to get A out if you mod P. So which means that this is multiple of P. So which means that when you mod P, this entry is gone. Because anything multiple of P are gone. Right? So this is what usually we call delta function, right? A delta function means that when you try something, on your coordinate you get 1, not on your coordinate you get 0. Right? So this number is exactly that delta function. Against P coordinates, first coordinate, you get 1. Against the other coordinates, you get 0. So this actually gives you mathematically the orthogonal basis of that space. Because what is the orthogonal basis? You align with your own direction, you're 1. You align with the other direction, you're 0. Right? That's orthogonality. Right? So this is exactly the same way to write coordinates. This is the projection. Right? So basically along the y direction, p direction, you project by this number. Along the q direction, you project by this number. Right? Because here clearly rho AB mod p, right, is equal to, is just this term mod p, right? Because the other term equal to 0. Right? So it's equal to YQ times Q mod A mod P. And this is equal to A mod P. because this is equal to 1. Right? So that's why I just said everything is everything is a linear algebra. There's nothing more than that. You just create a new basis functions. This basis function is just this inverse thing. Right? So that's why this is a great basis function. If you look at this number, mod p equal to 1, mod p equal to 1 and mod q equal to 0. Perfect. It gives you 1, 0 coordinates. Right? So this number, yq and q, this number actually, if you look at f, has the following coordinates. 1, 0. Right? And similar f, yp, xp, and this is your other coordinates. So that's why you should write out this projection. So when you have coordinate AB, you just set A times that coordinates plus B times that coordinate, you do the mod. So there's nothing different from your linear algebra book. Okay? This simple fact says Chinese remainder theorem hold. Because you can use relatively prime to create the coordinates, and this coordinate match with the coordinates you have in that table. Right? So this is the map. So 1, 0 is here. Okay? So this is proof of Chinese remainder theorem, that's all. Okay? And so later on I will try to mention to you why Chinese remainder theorem is important, particularly in the language later on, not just for RSA, but for pseudo-random number generation. You will see that a certain thing in such modular arithmetics become extremely beautiful that allow you to represent our coin flip perfectly. So that's essentially why it's a beautiful domain for pseudo-random number generation. Okay, so I have enough math here that I can just talk about RSA. The reason I'm very eager to put in Chinese remainder theorem at the early discussion, in part because they will show up multiple times, and if we have Chinese remainder theorem in our head, many things later on when you look is just utterly trivial. But if you go through the original domain, it's often very opaque because it didn't quite illustrate some of the underlying structures. Okay. So here is RSA. And A stands for Edelman. So this is Len Edelman of our department. The work was done at MIT. And so those are during the stage when public key encryption was just being proposed. And several teams, including Revest, Shamir. So Shamir is, we read about his paper on the secret sharing, and Len. So Len at that time, I think he just received his PhD from Berkeley shortly before this, and he studied. He's a computer scientist who studied in computer science, but essentially mostly studied number theory, algorithmic problem for number theory. And my own advisor, whose result I will also mention shortly, my own advisor, his name is Gary Miller, who is I think a year ahead of Len Edelman in Berkeley. So he is a mathematician who are interested in computer science. So you can see that during those days, the interdisciplinariness between math and computer science was quite common, largely in part because if you look at most of the computer science departments, they have two sources of origin. One is they break off from EE, The other one is the break off from mathematics. Right? So in fact, at USC, broke off from both math and double E at the beginning. But most of the place, they broke off from one of the two. And some school, the break off is not clean because every department wants this turf, right? Just like today, which department is most endangered to break off everywhere? Statistics. Right? Statistics, for example, USC has no statistics department. That's why you have statistics group in every department, right? Because it's a very common field, right? CS, called machine learning, and actually the largest statistics group is in Marshall. You would think that shouldn't be the case, should be in this building, but because they didn't have statistics department, it allowed Marshall to grow very fast in every other place, right? Just like computing, it's a very, those days, computing clearly on the rise, and different school department try to hold it for a while, and then eventually, once they break off, in every school they break off. And so he studied number theory in math department, but he's interested in computing, and then actually studied computer science, complexity theory, but interested in number theory, right? So you can see they are historically fairly unique in the sense that what they studied was very matched to what the field needs. But 10 years before their time, what they study is really peculiar. Right? So once actually I was talking with Gary, and my advisor, and let me mention a concept which, because we are going to hear that word a lot of time. Okay? So there's a term called quadratic residue. So quadratic residue means that, fancy name, called a number is perfect square. They call it quadratic residue. Number is perfect square. Okay? So in real number, in real numbers, every number is the perfect square. Right? Every positive number is perfect square in real number. Agree? Perfect squares everywhere in real number. So in complex number, negative number has a perfect square. Right? Negative 1 has roots. What's the root of negative 1? I, right? So basically, the complex number, everything perfect square, right? And then we go to the real number, all the positive things are perfect square, and we go to integer. How many perfect square we have? Infinite, right? An infinite number of perfect squares, but we don't have too many perfect squares. Right? We can even go with, you can see the density go down. Actually, the density went down far more fast than primes. Right? You have 1. What is the next one? 4. Not even 2. 9. 16. Right? So you can see the 25, they just keep on very quickly spaced out. But you can see prime number is filled with much high frequency right now. And it's forever too. Right? For example, this twin prime conjecture is just impossible for twin perfect square conjecture, right? That's why nobody studied twin perfect square conjecture, because it's not true. Right? Because clearly the distance between perfect square just become infinitely large, right? Because you have but when you do modular arithmetics, mod also bring back a lot of perfect squares. So this is the one thing I really want you eventually to get a sense, because perfect square is one thing we are going to use a lot. And it's not aligned with your integer, but slightly aligned with reals. So I want to say the real, the perfect square is a much cleanly distributed, right? You have larger batch of number has no perfect square. They're called negative number. Then you have everybody here has perfect square. They're called positive numbers. But in number theory, because it's the nature of modular arithmetics, the perfect square, if you just eyeball them, are much more randomly scattered. Which we will see in a few tables. Perfect square are much more, using our regular sense of ordering, they are much more scattered. unlike the real numbers, right? Real number has clean scatter, right? All has perfect square. So they also have density. Half of those are not perfect square because called negative number. But in the modular arithmetics, particularly if you model prime, later on we're using a fundamental fact that you have 50% of perfect square. And they're kind of scattered. So this actually is where actually eventual number theory become powerful in terms of random number generation. Because this modular arithmetic somehow scattered the perfect square. And it happened to be, my advisor was one of the early experts who are glued to the notion of perfect square. This is before people study random, encryption scheme and so on, right? So he told me once that the first time he gave a talk, I think in Toronto, in computer science, and he gave a talk, he said he didn't get that postdoc position because he said he gave a talk, instead of saying perfect square, he said quadratic residue. He said one of the members raised a hand and said, what the heck is quadratic residue? He said, that's the perfect square when you mod a number. Then the person just said, why don't you just call it perfect square? He said, we always call it quadratic residue. The other person said, we always call perfect square. So that's probably why he said, they probably think I'm totally outliers and no chance of teaching computer science here. And so he went to Waterloo, because his wife is Canadian, so eventually he returned back 19. So then he said that when Len graduated a year later, suddenly the perfect square, the connection with more emerging possible cryptography on the rise. He said most people began to hear the name. They don't mind it's called quadratic residue anymore, right? They can, right? So this is just similar things that when I was used to teaching numerical method. So that's why name sometimes matters, but sometimes it's important to know the concept. When I teach quadratic numerical method, and the first chapter I was reading, they have a name called Gibbons rotation. And it took me a while. I thought this must be a fancy concept, so I read very hard. And it turned out Gibbons rotation is just this rotation by theta degree. It's just this part of matrix that has a sine, negative cosine, cosine, negative sine. And that rotation, they have a name. And sometimes when they put down a name, it sounds very scary because I saw there's something really fancy going on there. But it's a very fundamental thing. But quadratic residue was heavily used. And I will continue to use QR as our representation, QR, later on, okay? Because they are beautifully done for number theory, and they really match our sense of randomness, okay? But for now, we don't need quadratic residue yet, even though eventually we want to make connections with them to draw the essence related with factoring, okay? So this work came out from very similar map that a group may create encoding, actually from Lagrange's theorem. Okay, so what they consider is n equal to pq. P, Q are large random primes. PQ are large random primes. So we'll talk about how to get them. And this is the function of generation. So remember in cryptography that the first function we have to generate. The generator creates the keys. In other words, generator creates the distribution of keys. Right? I think it's always better to think that way. Generate, GEN produces a description of keys, distribution of keys. Okay, it's not a single one. It's really a distribution of keys. So that's why in this domain, PQ are randomly chosen. And typically they have a security parameter. And in this particular case, the security parameter is measured by bits. Okay, so that's why you often hear when people say, I'm using RSA with 1K bits. 1K bits means that P and Q, when you write down the mean binary, is in the range of 1K. 1K is 1024, right? So 1K bits. And sometimes they use even longer bits, right? So when it first produced, the bits typically they use is 64 bits. So you can see how world changed. So they used to use 64 bits, 128 bits quickly. 512 was even take several regulations went to 512, and now it's in the sovereign, right? Because our computation device is just too powerful right now. Okay, so the log of P and Q. So they are the representation of our intuitive degree of security. And intuitively, the bigger the number, the harder for us to figure out the information. Okay, so that's the premises, which means there will be assumption I have to put on the table. Okay, and so this is the generation, but the generation has a second step. So this only generates the domain of message. So once we have this thing, we have message space is equal to the n star. We have our key space, both public key and private key is also in the n star. Okay, so they define the message space and key space, this n. So that's the first part of generation. So the second part of generation, this is related with this group theory parameters we used to discuss. So they will choose a random exponent called E. Okay, so this is a generation process, and they just publish E and N on the other page. A white page. So this is a generation step. So it generates two large numbers, multiply them, that define message space. And it takes another random number from the multiplicative group that define the public language. The key to the private language, the language of the person. Right? This is for encryption. Okay? So this is a generation. Simple, right? And I will talk about a little bit on how to handle this. So encryption using E of M is equal to M to the E on the M. So this is encryption. Okay, so those two are the public knowledge. So which means that everyone knows exactly the encryption scheme. Everyone knows how to compute it, right? Because when I have any message in the domain, so M is chosen from the n star, because that is my message space. And I just simply receive the power, and I return the value. Okay? So one way you can think about how do you do a message. For example, if I want to encode this, right, I may actually treat this an image, and I may convert that image into a numbers, right? Because I can just using the binaries of the Greek code as my number, right? So that's the encoding. That's my message of you, the class page. And then when I need to encrypt it, I literally just plug this number into M, and this number went up by exponent, and then I just output that as my ciphertext. Okay? So that's why back then when they run the experiments, they literally see a message, a picture, suddenly then I can still print it back to the picture, right? I can still just lay out my bits in the picture. Then you can see how much is scrambled. It is very scrambled. You will not see anything like this picture anymore. Right? Right. So this is a permutation. Later on we can prove. So this is a permutation of the N star. Okay? This is a permutation of the N star. It literally means that if you treat everything in the N star as image, it literally is a permutation of the image. Okay? The permutation is governed by this random element called E. Okay, so this is the encryption scheme. So then you may say, how do you decrypt? This actually we already knew from last week's class, right? End of last week's class. So to decrypt, we computed the following. Because E, GCD, E and N is equal to 1. It means that it exists E equal to E inverse mod N. Right. In other words, D times E is equal to 1 mod N. Okay? So this D can be computed just by the extended Euclidean algorithm, the standard GCD with extension. And the decryption we just simply raising, that means ciphertext. So C will be C to the power D. So one thing, actually, I think quite pleasing just by eye, that is the decryption in a schema is the same as an encryption schema, right? It's just raising power, right? So in some sense, remember when we think back of the old theorem of a one-time pad? On one-time pad, we said encryption and decryption are the same function. Remember, we just exclusive word with key. And then basically, there's a Shannon theorem saying that in every secure communication, the encryption and decryption are just some kind of permutation of that map, right? So basically, encryption and decryption fundamentally are similar in the same family of maps. And here, algebraically, very sweetly, they produce a map that actually encryption and decryption are in the very same format. Right, that is, they all just taking exponents. Right, they just taking exponents. Okay? So any question up to here? You heard yourself?
No, I just dropped my phone a little bit. PQ are known or not?
PQ, okay. It's important to, PQ are not known. When it's published, it's only published in this. So let's figure out what is known, what is not known. Okay?
But can't you get them?
They are there, so this is where the computation assumption is used.
Is it difficult because like I can imagine like n, if n is just multiplication of two prime numbers, right? So how many prime numbers, two prime numbers you can multiply to get n?
It's difficult, mainly currently nobody solved the problem.
Wow.
Let me put it this way. I don't have other better explanation why it's difficult. The only thing is that nobody solved the problem yet. So that's why,
But PQ not
imagine you solve the problem of factoring. You have two chances to be great. One is tell nobody and break out the bank and get money into your own bank. Or you publish it. Then people will give you a award and they will give you.
people will steal the money. Reviewers will steal the money.
So basically, there are two ways to do. If you actually factor a number, you can sell that idea and get rich, or you can be famous with that idea. And then suddenly nobody will use that. You will not get rich because nobody uses that scheme anymore. Okay, you will kill that scheme. So I don't have further recommendation, but currently the only assumption is that. The reason it's hard so far is nobody find a way to solve it.
So the hackers don't mention it.
Huh?
Hackers don't mention it, then
If hacker happen to figure it out,
we had to figure
why should you mention it?
it. Exactly.
Right.
Why would you mention
So that's why those are built upon. So, Shannon theorem fundamentally said you have to make certain assumptions. Right. That's why cryptography is really about ultimately what minimum assumption you want to make. Right. So those are, you can think as a result, the intermediate result. They are making very concrete assumption then to allow you to move forward. Right. But as a mathematical field, so that's why often the theoretical crypto is often separated from so-called practical crypto. Theoretical crypto lasts many years, in addition to figure out what other things one can do, right, such as zero-knowledge proof, identification, and so on, is try to fundamentally try to simplify the assumption so that you knew what is assumed, right? Because just like here, when you say, what did you assume? I give a simple assumption, right? It's hard to factor numbers. But I have to say it very accurately. That's why I will later on labor myself through, because I can't just simply say this is hard. I have to give you a sense of what hard in the mathematical term. Okay? So that's why RSA by itself, other than this, doesn't have a profound mathematical proof why this is a great schema, right? It mostly tied actually indirectly with the hard interfactory. And I would like to pull back a little bit using the quadratic residue to give us a little bit sense of its tie, right? And then using that to jump into a random number here. Okay. But the assumption, so that's why I have to be very carefully state what I assume. Okay. So let's first argue this is perfectly correct. But perfectly correct means that for every message, I encrypt, I decrypt, I get something back. Okay? So this, it just follows the group theory which we did last time. So that's why I said reading group theory formula as a justification of certain information schema is really a remarkable step taken in research. That formula was there a long time ago. Okay? So the perfect security comes from following, that when we decrypt an encrypted message, so this is equal to raising m to the a to the b to the d, m to the e and d mod n. So mathematically is equal to this. And last time we said by Lagrange theorem, Lagrange theorem is this one. Because of Lagrange theorem said that for every group element, if you raise power to the size of a group, it will give you 1 back. This also implies g of any x is equal to g x mod the size of a group. Okay, so this is really the main part that we are going to use. If you take elements, you go to any power, it's same as mod the out the size of the group, because this equal to 1. So when you mod it out, you just mod out the ones. Okay, so this is really the governing equation. So this means that if you have 2 elements, E and D equal to 1 mod size of G. Okay? I think I already made a little bit of mistake here, so let me correct my mistake. Okay. I actually say something on there. So if this condition is true, under this condition, so then basically this will be equal to e to the G to the E and to power D and mod mod G. Right. So this will be equal to G. Right. So any group element, if you can find two elements that they are relatively prime to the G, they multiply equal to 1, then if you reach this power, it will give you equal to 1. Okay? So this gives us the encryption and decryption formula, as I mentioned last time. Right? So we treat one equation here. So here I made one mistake in here. Let me write down the Z n star. Okay. I need this thing. Right. So this will be equal to m to the 1 mod EB mod Z n star. This is equal to 1. Because ED mod Z n star equal to 1. That's where it is at. Okay. So let me just think quickly. We know what is Z n star. What is size of this? So what is the n star? This actually we knew already if we take the Chinese remainder theorem. So that's why you can see Chinese remainder theorem is just utterly. I just give you the first quick look of Chinese remainder theorem. So remember in the Chinese remainder theorem we said if PQ are relatively prime, which is true in our case now, right? Because PQ are prime, then Zn star is isomorphic to Zp star and Zq star, right? So how many elements are here? P minus 1. How many elements are here? Q minus 1. Right. So which means that Zn star is equal to P minus 1 and Q minus 1. Okay. And this normally, number theory has a name called phi n. Phi n is defined to be the cardinality of the n star. Right. So just like here, the immediately field in this table tell you it's 2 times 4, right? That's 8. So P minus 1 times Q minus 1. Okay. So let me clean up my word a little bit. So instead of say Zn star, let me just say P minus 1. Okay, P minus 1, Q minus 1. Okay. So let me mention the Remy's question on what is known, what is not known, right? Right. We need to figure out what is known. So if you look at the generation schema, it creates distribution using P and Q to a larger prime. And it keeps P and Q private. So P and Q are private. If P and or Q was leaked, the whole thing breaks. Okay? And it releases N, so this is where clearly an assumption is made. That is from N, you can't efficiently get P and Q. What do you mean efficiently? Let's just say in our lifetime. Suppose I have key lengths to be certain things. Right? So this is a computational assumption, it's a gambling. Right? You gamble upon that in our lifetime you cannot break this code. Or lifetime means the lifetime of whatever the operation we want to deal with. Right? And so what else to keep it private? It will choose E and immediately make E public. Okay? But it privately derived D. Because D is just GCD of E against P minus 1 Q minus 1. So which means the person who generated the key know P minus 1 times Q minus 1, then is able to create E. Right? So here basically I will modify it. When I write it, I purposefully made a little bit of mistake just to simplify it a little bit. So here, instead of choosing E to be this, we actually choose E to be phi of n. Okay, so officially my message is not in Z n star, it's really Z, my key space is in Z phi n star. Agree with me, right? So those are the only thing, if first time without already say this, it will be too complicated for me to immediately put in. So this is where the key. So it's banking on several things. Banking on the fact that from the public knowledge, so what is public knowledge now? Is N and E. And you can't computationally get N and E, which involving P and Q. So D, decryption key, is the key that you want to hide. Okay?
So they don't break the code, they steal the keys.
So who don't break the code?
I mean,
If people steal the key, then you're dead.
They're done.
In public key, clearly, this just has to be the truth, right? If I tell people how I listen, then it's gone. The main thing is following. So partially I delayed my discussion about the crypto analysis and attack. In part because when we defend the system, we have to have the right language, what style attack we have. Right? So I think luckily today we began to talk about machine learning, right? Often we say a passive learner or an active learner, right? So what is passive learner in machine learning language? That is, they see samples, they see label of samples, they don't ask questions, and they build classifier, they learn. Okay, so for example, probably baby at early stage before they do a little bit active learning because they cry to force certain things, okay? But beyond that, they don't ask any questions, right? They listen, when they learn language, they literally just learn. You say something mostly just randomness, and occasionally few things labeled. You know, you just say apple, you just stick apple in their mouth, then they say, okay, these two things are mapped, right? So that is normally called passive learning. Right, you just observe as data go, some showed up with sample, some label, some you don't, and then you decide to classify the situation. Right. So this is really if you think as an attacker, this is really the most latest attacker. And easiest one, intuitive easiest one to defend against. Right, because this attacker does not spend much time just looking at the ciphertext flew by. Occasionally, government force certain organization to publish, to make things public. Then they will cross-check to see that it's matched. They got labeled data. Okay, but with public key encryption, the aggressive attacker can always do active learning. How you do active learning is even in a very serious way. They can choose a plain text, and they can create ciphertext in this language. Okay? So instantly you can see RSA has limitations. It doesn't matter whether you can break encryptions, break the factoring or not. You agree with me? Instantly, it means that the attacker can absolutely tell a message and ciphertext. So remember that when we try to define security in this ultimate sense, how do we talk about the encryption in security? We said, I will ask you to create two messages. Then we want to do the Turing test. Then you have to figure out which one was encrypted. You will pass the Turing test every time, right? Because you can just choose two different messages. Since you know the encryption, right? You knew exactly what ciphertext is. They're different. Because this has a permutation, which means they're different. So then you can 100% the score based on that definition. Right? So clearly this immediately means public key schema like this will not automatically pass Turing test. Right? Because everyone can create two messages. When you do the Turing test, you score 100%. Right? Because you knew exactly this message maps to this ciphertext. Every time this person couldn't do anything. Right? Because given upon you know the encryption schema. But at early stage, that's before the the thorough formulation of what is a secure encryption. And this actually partially why we are heavily still used. In part because when often people run them, they pad it. Right? So usually I take a picture of this, right? Because you are in a few thousand bits, right? Suppose you choose you choose 1K bits, which means your n is 2K bits, right? It's n 1K times 1K, and 2 to the 2K is a huge number, right? So which means that if I just take a picture and then do whatever the JPEG type of thing, I will create a number that will be far smaller than your 2K bits. So which means that when I encryption, sometimes you actually pad the rest by random thing, right? So to that degree, you are doing a probability encryption. Because every time I encrypt this picture, suddenly I encrypt a different number now because I pad the leftover with randomness, right? And it turned out this padding is universal. Namely, that the secure scheme for encryption in this rudimentary way can always be padded into an information secure scheme that makes it harder for you to pass Turing test. Right? The moment you can pad is a huge power. That is, I can have an encryption scheme that you have to not only get, because then when you choose ciphertext, you only choose a fraction of ciphertext now. The other part is padded. So you can't 100% predict, right? But on the other hand, it gives rise to a question to ask you. That is, if you look at this schema, where you produce the encryption, you may ask which bit actually is secure, right? Because every bit have different strengths. So next time I will show at least some bits are as secure as a schema. But in fact, early days when people hack RSA for other purpose, if they happen to embed the bits in the wrong place, people hack it out. Because certain bits are just not as secure. Okay. So that's why they gave absolutely promising solutions, but they really, what I think RSA did to crypto is they raised the bar of the game. And they also allow people to identify, see, just naively look at this scheme. They look so good, right? Nobody knows how to factor a number, how do you figure it out? But upon further analysis, then people realize they have a hard time to make a statement, to make a mathematical proof. Right. So this really, I think, profoundly the value of RSA. In part A, made connection with mathematical structure, like group theory, number theory, and it gave us a heavy domain to draw protocol from, right? And B is basically when people try to justify it, and people force them to justify much higher now. It's not like in all this time, you publish a scheme, then you just say, you break it. Right? I'm sending a message, you break it. Right? And if people couldn't break it in a few years, then you will say, see, this is the best scheme human ever made. But on the other hand, they were subject to much difficult examination because people suddenly demand them, because they're mathematicians, you prove we cannot break it. Right? Because they want to suddenly say, I want to give you a proof quality guarantee that you can't break it. So suddenly the burden is not on the attacker, it's on them, right? To mathematically prove this thing, you can't break it. And it's that attempt actually raises the quality of modern cryptography, because they suddenly have to go back to principle to define, as we go back then, right? What is information security? What can we say is slightly insecure, but you still cannot harness enough information, right? And how do you write out a test against all polynomial time algorithm, right? And it is that continued investigation and lead to, for example, later on, beautiful theory of zero knowledge proof, which is totally out of blue at that particular junction. But to this group, everyone was within short step to that question, right? But to public, zero knowledge proof is not, it's absolutely like a random question suddenly arises, right? So that's why when you look at such a schema, it's good to look at them with the right lens, and the correct lens is actually this is a maiden formulation of encryption. Right. In the simplest fashion, it has an explicit function, and if you harness what you know, what you don't know, and so in the rest 10 minutes, instead of fully going to mathematics, let me at least connect with some complexity issues. Okay. So when you have such a scheme, so what do we need? What do we call a good encryption scheme? Right. A good encryption scheme has two standards: computationally efficient and informationally skilled. Right? It was judged by these two things: how quickly you can produce such an encryption scheme, how quickly you can encrypt. Then against how hard it is for the adversary to break it. Right? So if you look at this scheme, computationally, what they need to do, they need to produce larger random primes efficiently. Okay? So this question was totally open before 70s. So this question actually was, so that's why you can see why the modern cryptography was born in 70s, because people had just figured out. And one of the main results is a result by Gary Miller in 75. So he wrote a PhD thesis with 21 pages, hardly any introductions, and whenever I talk to Gary Miller, he always say the reason you have to work on a good problem is that if you're bad writers, you have to work on a good problem. He said, I write a lot of introductions, and I would choose a problem that I don't need one. Right? So his thesis is just utterly short, 20-some pages with reference. And largely basically states, numbers here, the testing prime, it was an ancient problem, and so far no one can solve in polynomial time. So he's the first one gave a randomized algorithm for testing prime. Namely, his algorithm has the following property, that if a number is a prime, he will never answer its composite. Okay? If a number is composite with exceptional high probability, it will never answer prime. But occasionally it answers primes. So it has slightly flaw, you can see that. This is really the early generation of randomized algorithm, which went beyond quicksort. Remember our old friend quicksort? All we said is that quicksort can sort numbers in expected n times log n time, right? But you can still interpret the following. If you force it to have to solve n times log n time, then suddenly it's also become this type of statement. It will say, for any list with high probability I will sort it. Small chance it's not sorted. Right, that's quicksort actually. If you really flip the statement this way, right? When you say quicksort running expected n times log n time. But suppose you give it 10 times n times log n time. The best statement you can make is a quicksort, sometimes don't sort, but with exceptional high probability sort. Right? So he gave this testing prime in a similar statement. That is, if I give you a prime, so basically you give me any number, I will eventually call it prime or composite. Whenever I say composite, I'm 100% confident it's composite. I can even give you witness, it's composite. But miraculously, his witness is not a factor. That is a remarkable breakthrough in algorithm. Right? Because before people think about witness or composite, it's what? It's a factor. Agree? And he find a rich domain of witness that is not factor. He said, I can give you evidence that this is not a prime. I still couldn't tell you what is factor. So that's why they separated the hardness of testing prime or justify composite away from factoring. With high probability, I can tell you a number is not prime, but I can't give you, and whenever I say that, I actually give you a witness to say, I can prove to you it's not prime. And that proof does not involve in factor. Okay, so this clearly is a clean mathematical journey they did. So this basically provided the toolbox. So that's why Gary Miller continued to win major prize also along the way, because as encryption also go on, his results is continued to be also profound results, because it was the tool to enable this. So the first step when they do random number generation, they literally just do the most naive way. You choose large random numbers, you test for prime. If it's not prime, try again. And then the only result they bank on is there's enough prime. Right? So basically, in an ocean, you want a fish. If there's enough fish you like, mixed with the shrimp you don't want, you still go to the ocean, you dig out something. When you see a shrimp, you throw away, and you just go in. If there's enough density of fish, as long as you can tell them apart, you will get fish efficiently. Right? So that's where the random number is generated. Okay? There's enough good fish called prime in the ocean. The composite can be told apart. Okay? So that's how random number is generated. The rest you can see are trivial, right? Because the GCD is trivial. You can compute those things. The only one thing is not totally trivial is this computation, exponentiation. This exponentiation of a really large number. Right. And so how do you compute this? You can't just keep on saying m. You can't write a loop to say for I equal to 1 to n, e, multiply m. That will take exponential time. Right. So this actually is one of the early notion of divide and conquer algorithm. Right? Because in order to multiply m to the e, if e is an even number, you can just compute its square root and square it. So which means that you can drop one bit and with one multiply. And when e is an odd number, you can also take a square root of e minus 1 half and square it and then multiply the number again. Okay, so this is called an exponentiation algorithm based on powering up. Right? So essentially you just compute m to 0, m to the 1, m to the 2, m to the 3, m to the 1, m to the m to the m to the 2, m to the 4, m to the 8, m to the 16, and then whatever bits e has, you just multiply. Right? So that's the other way to compute this. So this basically shows this encryption scheme and the decryption scheme are both can be run in polynomial time. Right. So this is basically the computational justification. Is that in polynomial time I can create the primes. Once I can test prime, I can just go to the fish and shrimp game. Right. I just give me hardest some primes. Then I just multiply them, and then I can randomly choose e, and I can create my key that I just throw in the public domain. And when you do encryption, we can do a special circuit that is doubling up the multiply. So that's why there was a lot of VLSI implementation of RSA back then. Right? And then decryption, you get the same box. Okay? So this is a computational issue. The security issue is what I mentioned to you. It's not totally settled. But they made allusion to be hard and connection to be hard to the statement that nobody can find P and Q from n and a particular random number in the phi n star. Okay. And those statements are still widely open. Anyone who can make formal proof that testing factoring is as hard as RSA, I think instantly will get a PhD thesis with prize. Even that question is actually open. Can you prove that if you couldn't factor, you can't break RSA in even the traditional way? And that question was open. Okay, in part because E is given, and E may actually somehow have certain other information, and nobody can fully figure out what E actually captured right now. Okay. So next time we'll limit to E to square and allow us to connect with a quadratic residue, and I would like to eventually connect certain language with pseudo-random number generation, and it's actually the same schema. Eventually we can do so-called probabilistic encryption. That is an encryption scheme of public key nature that will pass the Turing test. So that's will be ultimate goal. We want to have encryption scheme that pass the Turing test. Namely, for any two messages you choose, you run through my encryption scheme, you couldn't tell the difference anymore. Computation. Thanks a lot. So we'll have homework due on Wednesday, and I will send out email